Hello.
Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the most awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Zeki Eker with us today. Hey, Zeki.
Hi. Hello.
How are you today on this November 11th?
Fine. I'm fine. How are you?
I'm doing awesome. Let's see. I'm in Phoenix. And so we're in the desert, and it is winter is coming. We have turned the corner. It's got gets fairly warm in the afternoon, but it's a little chilly in the morning and the evenings. And Zeki, where are you located at?
I am in southwestern part of Turkey, the city called Antalya.
Very nice. Very nice. Is it snowing there yet?
No, we are still in the Indian summer. You know, last days.
Yeah. Well, that's a term. Very cool. Very cool. Oh, nice. That's a pretty awesome bookshelf you got there behind you. You got a number of classics up there. I see. It's very nice. Very cool. And Zeki, what do you like to do for research?
I've done many kinds of the different researches. I started by spectroscopy, you know. Now, these days, I'm involved in calculating bolometric corrections of main sequence stars and so on.
Very cool. And that is going to bring us to this very awesome AJ article. It's open access, people. You can go get a copy for free, so go grab one. And a silent revolution in fundamental astrophysics. And Zeki, take us away.
Yeah, arbitrariness in the 0 point of bolometric corrections, you know, is taken to be as arbitrary. You know, the people thought that it is arbitrary, but this arbitrariness is taken about almost 100. But about 1 year ago, I discovered that you know it is not should not be arbitrary at all.
Okay.
And first, I have written an article about empirical bolometric correction coefficients for nearby main sequence stars in Gaia era. The title of my article.
Okay.
There, when doing this research of this article, I discovered that you know this 0 point of bolometric corrections should not be arbitrary.
Okay.
But somehow I couldn't convince. I couldn't convince the referee. So the referee asked to take out this stuff. I had to take out. Then after that, I collected this stuff and wrote another article called On the 0 point constant of bolometric correction scale.
Okay.
And this is the first time it's sent to AJ, Astronomical Journal.
Yes.
But somehow their referee again didn't like it, and he thought that I am bringing a new idea that is absurd, almost absurd. What about 80 years we are using these bolometric corrections and no problems happening? What as if I knew a new custom and a new thing that it is not necessarily correct.
Okay.
But somehow I couldn't convince the referee. Then I had to send it another journal. But somehow then I learned what was mistakes. I written much more carefully, you know, our colleagues.
That's always a good thing.
And there it is accepted.
Yay.
There it is accepted. Then after that, you know, because arbitrariness in the bolometric corrections causes people use different 0 point constants. Using different 0 point constants. So 0 point constants are used to calculate the luminosity of stars.
Yes.
Luminosity of stars, we need bolometric corrections. But arbitrariness causes the same star to be calculated different luminosity.
Sure. Different correction will give you different L
So
bar.
it needs to be standardized. You know,
Okay.
I introduced a concept, standard volumetric corrections. Then after standard volumetric corrections, need to introduce standard luminosity. Standard luminosity is calculated using standard volumetric corrections. Then what is the accuracy of standard volumetric, standard luminosities? So there was another article about that. Then, but about on the 0-point constant of volumetric magnitudes, I have written to some colleagues, including IAU. You know, this is, I am kind of defending IAU to take in a resolution 19. It is 2015.
Right.
2015. It's there is a here. Where is it? Somewhere there is a underline, you know, what you call, I cannot go down. Can you go down?
Sure.
Can you go down?
Sure. I don't know where you're at. Where do you want to go?
There is that one. There, the resolution, IAU resolution. This is actually, this is revolutionary. But somehow it's unnoticed. It is unnoticed. People are still writing about volumetric corrections are still arbitrary.
Well, you know, sometimes astronomy moves at its own time scale. It can be decadal.
But this arbitrariness, I kind of, you know, discussed it should not be, because arbitrariness, what kind of arbitrariness? The arbitrariness could be, you know, discrete arbitrariness. You know, some people say this, some people say this, but some people say infinite number of solutions. So if infinite number of solutions means there is no solution at all. You know, discrete arbitrariness is another thing. So I even proved that there is no discrete arbitrariness after this revolutionary document. And this revolutionary document even is shown to, you know, it tells you, can we cut the abstract? Can we get the abstract there?
Sure, we can do the abstract again. Sure. There we go. Got a little bit of a bandwidth lag, so we got to wait.
You know, this arbitrariness problem actually takes another problems. Volumetric corrections must always be negative. This is written in many books, and even Handbook of Astronomers. You know, Allen's astrophysical quantities. They are written, page 381. And volumetric magnitude of a star ought to be brighter than its V magnitude. This is even written everywhere. But somehow, you know, these are not correct anymore after IAU 2015 General Assembly Resolution B2.
Okay.
Should not be. You know, this is what this article, what does it? Really, we prove mathematically that volumetric corrections, you know, has definite 0 point, not arbitrary.
Okay.
And also that proves these two paradigms are also wrong. This is the article about.
Yes. Okay. So do we want to walk through some of that?
Would you like to see how can I prove that?
Sure.
Yeah, sure. Okay, we can go the next section.
Yes. Okay. Section 2.
Yeah, there. Of course, you know, this is the equation number 1.
Yes.
This is announced in the IAU 1915 General Assembly Resolution. It's exactly it is. It's from there. What they decided is the 0 point, the 7119742. This is what they decided.
Yes.
You know, if volumetric corrections has such a definite 0 point, you know, we already know, then it can be written in the form of equation 2. It is the same thing.
Sure.
You know, there. Then we can write about this is the absolute volumetric magnitude, and we can write the same thing about absolute visual magnitude. What should change?
Yes.
Only 0 point will change, because we don't see the luminosity of star, all wavelengths, but only certain, the visual, with the visible part. Okay?
Yes, I understand.
Then subtracting from each other,
Okay.
this is done in equation 4.
Right.
We will have equation there. LV, it's the visual luminosity divided by L, the log of that, plus the difference of two volumetric, it's the two coefficients, you know, the two constants there. They are well defined, well definite, because CV must be definite also. Without a definite 0 point, a photometry cannot be done.
Okay.
It is done. So for that, it is, we can prove there, it is definite, you know, that it's, where is their arbitrariness? C ball is definite and CV is definite.
Okay. That means
so there's no problem for that. We can go a little bit, continue.
Okay.
Then from the same equation, we derive equation 5. This is the same as the before, but it is just a log of change to the direct numbers. Their equation tells us LV must be less than L. Of course, you know, luminosity of a star is all wavelengths, and LV is small. No, just the visual part.
Yes.
So LV cannot even equal to L, always must be small.
Otherwise, it's a very interesting star.
So what makes the, you know, BCV there must be negative, of course. If it must be negative, and the C2 there's negative sign in front of it, even though it's a positive number, okay? Yes. So that equation is correct. But when does not work? If the BC minus C2 divided by 2, it's a positive number. If it's a positive number, LV becomes big.
Yes.
It is not even allowed to be CV equal to C2. C2 is a positive number. Why? Because C ball 711, it is bigger than CV, you know, visual magnitudes. So it must be a positive number.
I'm with you.
So of course, the BCV negative, it works, but also works from 0, the values from 0 to 0 to C2.
C2, correct.
It's positive numbers there. That's it. The second paradigm cannot be, you know, it's always been negative. No, it is not negative. You know, there could be positive. There could be positive numbers.
Okay.
And here, then after that, you know, if why people said, well, why scientists said the second paradigm. What was the second paradigm? I remember that. Can I see the abstract?
What would you like?
Abstract.
Abstract again. Yes, we'll go back to the abstract. Sounds good. Sounds good. Okay. Just wait for the bandwidth.
Volumetric magnitude of a star ought to be bright on its V magnitude. You know, this is if you take a C2, you know, that is the 0 point constant of the volumetric corrections. If you take 0, that condition occurs.
Okay.
If BC is negative, and M bolometric magnitude must always be smaller, so it's brighter. But now equation is telling me this is not true, because there is a positive BCR positive. Positive BCR possible now.
Okay.
But many books says the opposite.
Yes. Okay.
And this is done in absolute magnitudes in section 2. In section 3, I've done the same kind of discussion using apparent magnitudes.
Yes.
And ending up in the same conclusion.
All right.
In using apparent magnitudes. It's the same, even the same equation. Can you see the last equation there?
Equation 6?
No, 7.
7, let's go to 7.
7, go more.
Yeah,
Six.
yeah.
And then the last one, 10, 11. Equation 11.
11.
End up equation 11, the same as before. We discussed the same equation.
Yes.
I ended up in the same equation. This is the equation I tell that BC V values it's possible from 0 to C2. It's positive numbers are possible. It's very clear here.
Okay.
It's very clear here. So it's no problem, not just only absolute magnitudes, but apparent magnitudes, apparent magnitudes also telling me the same thing.
Yes.
Let's come to discussions now.
Okay. Where are we? Discussions. Vega.
There.
Everybody loves Vega.
Discussions.
Not everybody, but I do.
One counter argument, the people are arguing against, telling me that IAU, International Astronomical Union, did not set the bolometric correction scale.
Yes.
It defined only the bolometric magnitude scale set to SI irradiance, that is M ball, F ball, and luminosity. Absolute magnitude M ball, L ball, yes. Whereas photometric magnitudes are independently defined by standard stars.
Correct. Yes.
And that's why they say IAU could set easily the former, but not later, such as the Johnson V system, because IAU did not set the BC scale. Sure. Nothing new could be claimed about it, especially about the arbitrariness attributed to BC scale that has been used for about 8 decades, almost 100 years.
Almost, yes.
This is what their argument.
Yeah.
It's the main argument.
Okay.
But this argument, advocating the BC system used before 2015 for about 8 decades is invalid now. It's not true anymore.
Okay.
Equation 9 could be generalized for any photometric system. This is the equation. Could be any. Could be generalized to any. And it can be written in the absolute magnitude, M ball. The next equation 13 is also true.
Sure. Okay.
So there is two ways, what they say. Subscripts indicate a filter in a photometric system. Apparently, whether it was intentional or not, the resolution conducted by IAU was the most easy and logical solution that time. This is because it is illogical to set innumerable 0 points for BC.
Oh, sure. We know 400.
If you go there to set BC in a photometric band, there are many. This is illogical, but
well, glad you're having fun. Okay. Keep going.
It is obvious in the equations above, fixing the 0 point of bolometric magnitudes by equation 6. You know, we did be up. You know, this is the resolution. Fixes everything. It's one step.
Mm-hmm. Any given correction.
Why should we go to every volumetric correction for different bands?
Okay. Mm-hmm.
So here it is, arbitrariness of the BC scale was removed automatically after fixing this C-ball.
Okay.
But before 2015, there was no C-ball, value of the C-ball, 7.1 there. If there is no such a, then it is arbitrary.
Yes.
People are right, because there is no number for that. But
right.
after 2015, 2015, we cannot use this, you know.
I understand. Mm-hmm. I'm with you.
What else?
8 points.
So
Oh, we got
this is mathematically proves section 2 and section 3, but you see, you can see with that another we calculated the volumetric corrections in the Gaia G band, Gaia GBP band,
yes.
Gaia band, Johnson V and Johnson B.
Mm-hmm.
These are the coefficients. These are the equation. You just equation there is written somewhere
14.
there.
14.
This is BC equal to AB. You know, the X is there. Log T effective.
Mm-hmm.
Just give me the T effective for star on the main sequence. I will tell you what's the volumetric correction in any band in this.
Coefficients. Okay. Mm-hmm.
Coefficients there, and the errors in the coefficients there. You know, of course, the number of stars used there, 402, and of course, Johnson B and V is less because not every star is observed. Because that's the reason, but
sure.
The guy observed more stars. And there, the equations there is written on the single frame. Can see? Yeah. The volumetric correction, magnitude, different bands. They cut each other at log T effective 4. That means 10,000.
Yes.
Degree Kelvin there. This is the Vega system of magnitudes. Because Vega system of magnitudes, colors must be 0. That was the reason.
Yes.
So that proves also what we, you know, the other photometric systems has definite 0 point. So we don't have to worry about that. So using with the volumetric magnitude 0 point, so problem are solved totally.
Mm-hmm. All right. Well, I like total solutions.
Total solutions. And this is very important because the other paradigms are misleading and misleading astronomers. Not because these are used in many books. Okay, teaching. Maybe high school teachers, maybe university teachers, university instructors using these, the paradigms, they're still teaching them.
Sure.
The problem is there.
Sometimes astronomy moves slow.
I added some kind of advisors, here the authority maybe who should involve solving for that, but somehow, this is asked by editor to remove that part because article is not about that. Article is just scientific. So we just prove scientific. But look at this. What is the gain for C-ball, the determination of C-ball? What is the gain? What is the benefit?
Okay.
Benefit is explained in there. I took, there is three ways to calculate luminosity of a star, because luminosity of a star is not observable. There is no telescope, there is no detector to see all wavelength. Neither M-ball, volumetric magnitudes, or luminosity cannot be observable. It needs to be calculated from observable parameters.
Sure. It
needs to be calculated. So I calculated some example stars there. If there is a direct method to calculating it. This is using binary stars, especially the detached eclipsing binaries.
Okay.
Detached eclipsing binaries, one can obtain radius of a star and the effective temperature of a star. That's enough for calculating luminosity of a star. There's a Stefan Boltzmann law. Surface area multiplied by flux of a black body, the temperature there, you can get the luminosity.
Okay.
But this is only limited to detached binaries. But astronomers need to calculate the other stars. We need them. So there are methods. The old times, they used mass luminosity, mass luminosity.
Yes.
So mass luminosity relation of main sequence, for example, right? You get the mass of the star somehow, you can calculate the luminosity, but this is not very accurate now. But another method is use bolometric corrections. With these secondary methods, using mass luminosity relation or bolometric corrections cannot be accurate as Stefan Boltzmann law. Direct method is most accurate up to now. Five different bolometric correction to effective relation. Now we can calculate luminosity of a star almost 4 times more accurate.
All right. So factors of 4. Okay.
This is the contribution. This is the great achievement.
Okay.
And this is because accuracy is not needed only stellar astrophysics. Accuracy is needed also by galactic astronomy. Extragalactic astronomy.
Sure.
Because when we determine the luminosity of stars, we can determine the luminosity of galaxies. If the correct luminosity of galaxies, that means correct distance of galaxies. Correct distances means Hubble law can be corrected. And Hubble law, even cosmology is affected. So this fundamental astronomy is affected not only stellar astrophysics, but all other branches. So that's the reason this article is very important.
Okay. Very good.
What do you think?
I think I want to say, Zeki, thank you so much for walking us through your provocative article. Let's call it that.
Provocative, yeah.
If not the article. Yeah. Very cool. Very good. So thank you. And so let me ask a little bit. So where do you think this topic goes over the next 2 to 5 years or so?
I expect more than 2 to 5 years. I expect, not me, perhaps the other astronomers should take it, because I'm almost to retire in a few years. But other astronomers will take it to calculate luminosity of each star in our galaxy correctly, using correct bolometric magnitudes, and even increase the number of bolometric correction relations there, BCT effective relations, to increase this number and calculate luminosity of stars even less than 1%. It's very accurate. Then after that, go ahead to calculate luminosity of galaxies. And even go to correct Hubble law, Hubble constant. And this way they can solve even Hubble tension. The problem of Hubble tension can be solved this way.
All right. Yeah, that's a tension. Okay, that's a totally different topic, but yes. Very good. All righty, Zeki, well, thank you so much for walking us through your very lovely AJ article. Appreciate it.
I hope I explained well. It is clear now, because many people out there are still not believing. They say bolometric corrections are still arbitrary.
Oh, there's always a variety of opinions on a given topic, I'm sure. So All
This
right.
is, yes.
Okay, very good. That will do. So thank you very much once again. And everyone, I hope this made your astronomy today just a little bit lighter. And we will see you on the next one. Bye-bye.
Bye.